There's going to be two ways to do this. I'm asking you to come up with one of them all by yourself. They're both valid methods, but one is going to fall apart when the numbers get very, very big and when the numbers get very, very small. I'd like all of you to have an answer on your paper somewhere for this. If I gave you $1 million to come up with an answer that was correct, you'd work fairly hard, I would think, to make sure that the answer was correct. You have a question? Okay, I'll come back to you in a minute. I want everybody to take some time with this. I'm basically asking you to add 42 million and 380 million together. Basically what I'm asking you to do. That's what you should see when you see that. Two large numbers that are being added together, and in some way you should be able to add those numbers together. In a minute. All right. What I see on most of your papers. First of all, what answer did you get? Yes, please.
4.22 times 10 to the
4.22 times 10 to the 8th. Yes, which is 422 million?
Yeah.
All right. So a lot of students, and maybe 10 years from now, if you're asked this question, you may not remember this method, but you'll think to yourself, you know what I can do? I can write these numbers out. Add them together. And change it to scientific notation. What I just did, I would expect you to walk into this classroom with already being able to do, based on what we've done so far this year. What I am going to offer you is a way that will probably be faster and will certainly hold up when our exponents turn into 30s and negative 24s and things get very large and very small. You don't have to copy this down, but I want you to follow along with something that I'm about to do. I am going to take the number 3,428. I'm going to write it 10 different ways. Pay attention, please. I'm going to write 3,428 as 342.8 times 10. I can do that, right? It's still 3,428. I've just pulled the power of 10 out of it. I can also write it as 34.28 times 100. If I multiply 34.28 times 100, I get 3,428. I'm also going to write it as 3.428 times 1,000. That quantity is 3,428. I'm also going to write it as 0.3428 times 10,000. Those are all the same quantity. I have not changed the quantity, I've simply changed the form. Now I'm going to rewrite each one of those numbers. 3,428 can be written as 3,428 times 10 to the 0. 10 to the 0 is what? 1. I'm using the multiplicative identity property. Anything times 1 is itself. I'm going to write 342.8 times 10 as 342.8 is 10 to the first. 10 to the first is 10. Anything to the first is itself. I'm going to write 34.28 times 100 as 34.28 times 10 squared. These are all the same quantity. I'm just going to change some numbers to make life easier for myself, and you'll see why in a minute. 3.428 times 1,000 is 3.428 times 10 to the third. And finally, 0.3428 times 10,000 is 0.3428 times 10 to the fourth. I'd like you to notice something. When I go from here to here, this number, the coefficient, goes down by a power of 10. From 3428 to 342.8, I've gone down by a power of 10. My exponent, therefore, to make up for it, has to go up by a power of 10. When I go from here to here, my coefficient went up by a power of 10. I went from 0.3428 to 3.428. Therefore, my exponent had to go down by a power of 10. It's a balance that must be maintained. Is everybody okay so far? I know you just got in from outside and this is a little dry, but we're going to use this to make our life easier. Another method for solving this. 1, rewrite. This is going in your notes. Rewrite our problem using the same exponent. And I'm going to say, use the higher of the two. I want you to understand what we're doing, but eventually it will turn out to be a process that you could do in your sleep practically. In my original problem, I have one of my numbers is written times 10 to the 7th, the other is written times 10 to the 8th. I'm going to take the higher one of those, and I am going to rewrite the entire problem, and you're going to see why in a minute. This will all make sense in a minute. My second number is already times 10 to the 8th, so I'm going to just put it in the problem. So far, I haven't really done anything magical. I've rewritten the problem. Higher exponent, I rewrite the problem based on that higher exponent. I'm adding these numbers together. Now, my 4.2 times 10 to the 7th, I had to take this up by a power of 10 in order to make it times 10 to the 8th. So I'm going to bring this down and write it as 0.42. Now, I want you to take a second to appreciate what just happened. My numbers in this problem lined up this way. When I wrote this out in standard notation, this is the way my numbers lined up based on our powers of 10. When I rewrite the problem, I've got to get my numbers to line up the same way, and that's exactly what I just did. I got the numbers to line up the same way. And I maintained the problem as a scientific notation problem. We're going to add these numbers. 2, 2, 4, bring down the decimal. 4.22 times 10 to the 8th. Same result. But the first way that we did it is going to fall apart once we get to really big numbers. The second way is easy to deal with really big numbers. And we're going to do 2 more examples, and I'm going to show you that. And hopefully we're going to finish the textbook work associated with this item. And I'm here to help. Everybody good? Second example has to do with subtraction. Let's see, we're going to take 3.4 times 10 to the 30th. We're going to subtract from it, 6.2 times 10 to the 29th. We'll try that. What's higher, 29 or 30? 30. The problem is going to all be done 10 to the 30th. 10 to the 30th. We're subtracting 10 to the 30th. 3.4 is already written times 10 to the 30th. The other part of our problem is not. This has to go up, so this has to go down. 0.62. Now I can perform my subtraction. I have to borrow from here. 10 minus 2 is 8. I have to borrow again from here. 13 minus 6 is 7. 2 minus 0 is 2. 2.78 times 10 to the 30th. You're going to be experts on this. You'll be quick at it after a while. There's one more issue that might take place. One more addition problem I'd like to show you. We are going to add 9.7 times 10 to the negative 20th plus 8.1 times 10 to the negative 21st. Which is bigger, negative 20 or negative 21?
Negative 20.
Negative 20. Automatic. Boom. I'm not even thinking right now. I'm just setting the problem up. And one of these numbers is already negative 20. Look at all I've done, and I really haven't done much of anything yet. Let's set the problem up. This has to go up to negative 20. Okay, once your negatives are involved, you kind of have to think about that. This has to come down to 0.81. This is going to produce a problem that's easily solvable. I add them together. 15, 10.51 times 10 to the negative 20th. What's wrong with the answer? I'm sorry? Yes, the numbers are correct, but what's wrong? Yes.
The decimal place is in the right spot because that's doing 1 digit to the left of the decimal.
Exactly. That's not correct scientific notation form. That's correct scientific notation form. But to do that, this had to come down. So this has to go up. Times 10 to the negative 19th. Not only did I have to use what we learned to set the problem up and solve it, I had to use what we learned to put our answer in correct scientific notation form. I had to perform that operation twice. I'm exhausted.